Hello, everyone. Are we live now? Yep. Excellent. Hi. So let me get this up. Hi. So my name is Alexander Baker. I'm currently a senior data scientist at KPMG. And if I remember giving a talk previously on this data science cast conference, and I wanted to create like a part two to the talk that I previously gave. So in my previous talk, I kind of went over the basics of how to set up your machine learning algorithms, some of the basic algorithms, how to execute them, how to optimize them, evaluate them. I wanted to dive into a more advanced topic on, in this case. So I titled this a deep dive into deep learning. I thought that was kind of catchy, but in reality, it's mostly just establishing like the foundation of your deep learning journey and essentially where to go from there. But I'm hoping by the end you understand the basics and a couple of flavors of neural networks and how to properly apply them and where to go next. So I guess we should establish what deep learning is in the first place. So essentially, deep learning is a set of machine learning algorithms that are modeled after the human brain. So if you don't know how a neuron works, they take in inputs from other neurons, process them, and then they bring those inputs down through their axon, and then deliver an output to another neuron. And essentially, you can kind of see the way these neurons are interacting in this nice little GIF over here. They're taking in inputs from previous neurons and sending them to other neurons that are using those inputs and creating their own. So you can so this algorithm is built to be can be modified and built to be a more sophisticated version of machine learning compared to what we previously had, and is very well adjusted to be used for larger data sets. Now you might be wondering, this is a really cool advanced algorithm. I wonder who like this probably originated not too long ago, but in reality, the first neural networks were created in the late 1950s. However, the reason why we're seeing this renaissance of deep learning and this renaissance of neural networks right now is our big data technologies have really started to expand, especially in the last 10 years. And because of that, neural networks have been, we essentially realize the maximum potential for neural networks. And that's why neural networks are kind of seen as the future of machine learning right now, because as big data technologies advance, so will neural networks. Now, I guess I should stop and ask any questions really quick. No, just getting started. No questions. Sorry, you guys. We're going to be bouncing around quite a lot. I have code. I have to check the chat for questions. I have the presentation, but we'll continue going. We have a lot to get through in a short period of time. So this is one of my favorite diagrams. You might be wondering, well, what's the difference between neural networks and traditional machine learning? Well, a neural network or deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. So you can kind of think of artificial intelligence as a general category for people using computers to mimic human intelligence. Machine learning is a subset of that category that essentially extracts decisions from data and don't really have the necessity to be programmed. And then of machine learning, we have deep learning, which is a subset of machine learning that mimics the human brain in its architecture. Excuse me. So the difference is deep learning typically is known to require far more data far more data than traditional machine learning methods like random forests. And they're known to be a little bit more sophisticated in their architecture as well. And on top of that, they're able to very readily pre-process unstructured data like images without the need for excessive human intervention. And it should be noted that like a big warning with this is that these algorithms are black box. Now, what I mean by black box is that it's very hard to dive into a neural network and understand exactly how it makes its decisions where it does. And this is one of those disadvantages of deep learning that you need to heavily consider if you want to use it for your projects. Like if transparency in decision making is a necessity for you and really helpful for you, neural networks for your project are probably not the way to go. And especially if you don't have enough data, neural networks are very computationally expensive and require a lot of data in order to be trained properly. So if you don't, if you they're always worth trying, but if it's very rare that on small data sets that your neural network will outperform something like XGBoost. So just something to keep in mind. Now, let me check the questions before we dive into the terminology, because this is where we really get the name. Artificial intelligence came out in 1980, while neural networks in 1950. Exactly. So that is true. So it's possible that the mathematics behind a neural network came out in 1958, but it wasn't really recognized as like the modern neural networks that we have now. But basically, like that's when the first papers started to originate. Yeah, my mistake for misleading. Yep. If we have no questions, it's time to really get into the meat of this. So these two slides consist of all the terminology that are very important for neural networks, and I will be consistently using these terms, and you'll see these pop up, especially in the code as well. So you can kind of consider a layer as a collection of what is known as nodes that comprise each portion of your neural network. So your neural network is essentially constructed in layers, and you'll see a visualization of each of these terms later. And a neuron is each individual node that essentially takes in the weights, adds a bias, and then produces an output that moves to the next layer. And forward propagation is essentially like the act of how the neural networks continue to produce these outputs, send them to the next neuron. That neuron produces outputs all until the output layer, and then that output layer produces a comprehensive output of itself. And then back propagation is essentially puts the learning in deep learning. It it takes an output with and then uses some type of metric to create a cost, and then essentially adjust the weights accordingly by using that cost. I'll dive far more deeper into back propagation later. Activation function. So this is where neural networks kind of get creative. So if you see the structure of a neural network, you'll notice that it looks a lot like a line. It looks very linear. So activation functions essentially choose like which neurons fire and which don't, and that adds this layer of non-linearity to the neural network to give it a more sophisticated method of producing outputs. And then, as stated before, the loss function is essentially how the neural network determines or how the neural network validates its prediction against the actual data. And the optimizer is how a neural network uses that loss function to update the weights. And then we have our input layer, our hidden layer, and our output layer. You can essentially think of this as the three major components of a vanilla neural network, or of a vanilla neural network. The input layer will take the input dimensions of your data, and essentially create an output that will send it to the hidden layer. The hidden layer takes the inputs from the input layer, and then creates outputs that sends to the output layer. And the output layer will take those inputs from the hidden layer and then produce an output. Now, I should note that there can be more than one hidden layer within a neural network. It doesn't just have to be three different parts. In general, many neural networks have numerous hidden layers that can increase your increase accuracy or increase the sophistication of your architecture. Can, it's not always. So so yeah, you can think of this in like a very basic example, but there's more than just, but you can add more than just one hidden layer in your neural network. Now we get into the three other terms: batch size, epoch, and iteration. So essentially, when you're training a neural network, neural networks are very, as I said, they're very computationally expensive to train, and a method to reduce that computational time is by splitting the data up into different portions and training one portion of the data at a time within your neural network, and essentially until the entire data is trained over. Now, this is called, each part of your data is called a batch size. An iteration is the number of batches you need to go over your entire data set, and an epoch is the number of times you train over that data set in its entirety. Because typically you don't want to go over with a lot of neural networks, they don't go over the data set only once. Like, you want to continue to do it sometimes hundreds, maybe tens, hundreds, sometimes thousands of times, but you also want to be careful of overtraining. Now, that was a lot of information. You all probably have a ton of questions, so let me check. Excellent. Doesn't seem like we have a whole lot of questions. So it's time to visualize neural networks as a whole. So you can consider this an execution of each of the terms that we went over previously. So this is what I call the vanilla neural network, also called the artificial neural network. In this particular example, the layers will be fully connected. And what that means is that the input of each different node goes to the output of each different node becomes the input of each node in the preceding layer. So you can see this is an example of a fully connected neural network. You can see that this is the input data. It goes to each individual node. That input is processed and then output, and then that goes to each individual node here. And then that is sent to the output node, and an output is produced. So this is essentially what it means to be like fully connected. The data from one layer becomes the input. The output from one layer becomes the input of another, and then you can see that once we reach the end, we input our basically the output and the validation of the actual data are inputs in what is known as the loss function. From there, we calculate the loss, and then we go through a process called backpropagation that will essentially take the derivative of that loss function and take a derivative of that loss function, have a particular learning rate that you can establish, and essentially update each of the weights using that difference in the loss function. So that's essentially how backpropagation is done. The math looks very complicated, but if you see it actually executed in code, it's pretty simple. But basically, like, that's the way the neural network actually learns. They take that loss function and then update the weights backwards all the way until the end, and then the neural network is then rerun. So, and you can kind of see what happens within each layer. So at the beginning, I said a neural network or a neuron is very linear in its output, and that's why we have that activation function. So you can see we take our inputs, which are the x's, we multiply them by the weights. We then add biases to each of those x times weights, and then we put those in an activation function, and that becomes our output. So so without this activation step, you can see that this would just be a simple line, y equals mx plus b, as simple as it gets. But we don't want that simplicity in our neural network. We want that element of nonlinearity, so that our neural network can adjust more readily to higher volumes of data. Yep. And then we basically do this until the weights converge, or we run out of data, or we choose to end the number of epochs. So this is like the basic architecture of everything we discussed in action. Now let me check the chat to see if we have any questions. Nope, I don't believe we have any questions. Excellent. So I guess we can move on to the next one. So what happens when there is a dependency between different inputs? You can think of some examples like time series or text transformations. And what can we do to essentially adjust our neural network architecture to account for these scenarios? Well, this is where recurrent neural networks come in. Now, this is a special flavor of neural networks that essentially, that on a high level, they take into consideration the trainings from the previous from what is known as a previous state, and then implement the results from a previous state into a current state, in order to or input the results of the previous state, combine them with the inputs of its current state, and then it will produce the results of that current state. And essentially what we have here is it's taking into account that dependency between the previous value and the current value in order to create the current cell state. So going through this one by one, the input is multiplied by it starts out simple. The input is multiplied by its current weight from the neural network, and then that is added to the previous state multiplied by what is known as the recurrent neural network weight. And that's essentially how we get that consideration for the previous state inside. Once that is found, it is placed within a tanh function. And then, oh yeah, I can't forget to add in the bias. Once that's found, it's placed within the tanh function. That tanh function is basically used as like the de facto. It's basically used as the de facto function for a lot of this time series analysis. My assumption is because it's a simple normalized state to go between -1 and 1. So that's probably why, like, a lot of the math centers around this when it determines the value of a recurrent neural network. But then once that's placed into the tanh function, it is then multiplied by what is known as an output neuron weight, and then once it's multiplied by the output neuron rate, we have the current state, and then that state is used to use for the next state, and then this process is repeated until the end of our step, and we want to redo it with a new epoch or whatever we want. Now, you may have realized something by going through this recurrent neural network. It seems to be pretty short-sighted. We're only taking into account the input from the previous state, and it kind of forgets everything. So what we have, this is going to be like a very long slide, so bear with me. But long-term short memory networks are the evolution of, or long short-term memory, my mistake. It's the evolution of these recurrent neural networks. And essentially the reason why these are more advanced is that they're able to take into consideration the overall context far better than the vanilla recurrent neural networks. Now, how it does this is it has multiple different gates, and it filters very closely what it lets in and what it considers as a part of the final output. Now, it has three different gates. It has the forget gate, the input gate, and then the output gate. And essentially, what each of these does is it filters the cell or the neural network and the information on each different level. So when information it goes into the long-term short memory cell, it first goes through what is called the forget gate. Now, the forget gate will take the previous state and the current, and essentially choose which information would be best. It creates this filter using a sigmoid function in order to determine which information it wants to remember from the previous cells. Then we create a candidate cell or a candidate cell state, which essentially determines which information we might want to let into the current cells. And then that is multiplied by the input gate. The input gate, it's similar to our forget gate, where we essentially take our input and it's very similar. We take our input, but with some different input weights, and then we create our feature filter for the we create our feature filter for the essentially candidates that we would want to consider, and then we create our cell state from our filters and our candidates and our previous candidates, and then that is aggregated and multiplied by the output filter, which essentially creates our current which essentially creates the cell state that we will use for the next LSTM. Now, that was a lot. Let me see if there's anything. Question keep getting lost. Make sure aka chat. That is not for me. They're under ask a question. Oh, sorry about that. Still getting used to the platform. Where is the ask a questions? Questions are under ask a question in the question section. I am so sorry. I am looking for the ask a question sections. I do not see it. Sorry about this. Question section. Right next to the donate. Oh, goodness gracious. Donate. Oh, sorry about that. No wonder why I couldn't see it. How to know if I have enough data for a neural network. Ooh. Yep. Sorry about that. There was a pop-up that was hiding it. Behind this. Yep. So I have it up. How to know if we have enough data for our neural network? Excellent question. Typically, it's difficult to tell. You would basically it's worth testing a neural network even if you don't think you have enough data, just to see how it would react to your current input. You definitely there's no like hard cutoff. Like this is how much data you should consider a neural network. This is how much data you shouldn't. However, when you are dealing with a lot of data, it's important to like consider neural networks as part of your pipeline. What I would actually say is the most important factor in determining whether you should use a neural network or not is asking what your problem is. Like if you want to have a deep dive in which factors directly affect how a certain bank decides whether or not to produce a loan, and which factors contribute to that, you wouldn't want to use a neural network for that, because it'd be very difficult to essentially look in depth to how the neural network conducts its decisions. So I hope I answered your question. Basically, it's always worth it to test most things in your arsenal to see what produces the better result. However, if you're dealing with big data, you may want to consider a neural network. What is the most used activation functions in the neural network space? Another fantastic question. I would say that I see the ReLU function used a lot in the activation in used a lot as an activation function, and with ReLU, basically the reason why is that you have a zero and then you have a line that goes like this. And the reason why that's used is that it's a very convenient way to maintain that structure without. It's a very convenient way to maintain that structure while also having a non-firing range. But this is the most basic one. There have been tons and tons of different activation functions that are still being developed that are considered better than ReLU. Like there's leaky ReLU, which has a tiny negative value that lets a little bit that lets a little activation slip by when it doesn't meet the requirements or the fire requirements. And then there's I should note that the main difference between like an output layer and the rest of the layers is that output layers have special activation functions that kind of fit the output into a certain paradigm, I should say. That so like if you like an output, if you were to have an output layer and you were predicting like a binary value, you'd want a sigmoid as your activation function. If you had an output layer and you were predicting multiple values or like multiple categories, you would have a softmax. But yes, the activate. But yeah, ReLU is what I would say is what I see used the most. But ReLU is what I would say used the most. On the final layer, it's on the final layer. I typically see sigmoid for soft or for. I typically see sigmoid on the final layer for binary or softmax for multiple categories. And then people use whatever they want to for the continuous. Like in time series, it's tan H a lot. Sometimes people don't. Sometimes people just use the base activation functions as the final layer. So it's up to you. Excellent question. What do you think about trust issues the NNs bring due to being a black box? Another fantastic question. This is a huge point. So this is a huge point of contention in AI and ethical AI. Yes, it's a very hotly debated topic. What do I think? I think that I do personally have trust issues is a good way to put it. I personally like to make my machine learning as transparent as possible. So I only use neural networks on the occasions that I essentially have to, or if I have like a ton of data that where it might benefit. But it's very important to consider like the data that you're inputting inside of your machine learning model. That's one of the main points of ethical machine learning. But yeah, neural networks are the main point of contention in that whole issue. In my opinion, I would prefer at the very least to be very transparent about the data inputs that you put in your machine learning model, and how you think, like a proper analysis on how you think those inputs may affect the neural network's decisions. But basically, yeah, yeah, excellent question. You can have an entire debate about ethical AI over neural networks in particular. Please, can you give further explanation on the activation function? Yep. So basically, the activation functions work by determining whether or not, by basically providing the neural network's output using the neural network's output as an input to determine whether they fire or not. So similar to how neurons work in real life, they need to reach a certain threshold before they can produce their output. And what something like the ReLU function, actually, let me show you this real quick so you can picture it. So something like the ReLU function can essentially, if the neural network doesn't fit like a certain criteria, it'll just end up as zero. And then if it does, it will continue its output like this. And essentially, this is not only meant to further mimic the way the human mind works, but it essentially also provides this layer of sophistication in the outputs by getting rid of that linear property that a lot of neural networks have. Now, ReLU isn't the only one, as I said, and it can all and on top of that, they're used to kind of format the outputs in a proper method that can be readily interpreted as certain decisions. So I hope that helped, that little bit of explanation, and so you can actually visualize what these activation functions look like and how they operate and how they add that layer of nonlinearity. Can you share a good resource for deep learning? Yes. Let me show you this. This right here. The books on my shelf aren't for show. This is possibly one of the best books in all of data science, not only for traditional machine learning, but deep learning as well. If you want to see what the math looks like in depth, this book will help you out. There are better versions of it. There are newer versions of it, but this is one fantastic resource if you're curious. Oh yeah, by the way, sorry, this is Hands-on Machine Learning with Scikit-learn and Tensorflow by Aurelian Geron. Excellent resource. Couldn't recommend it enough. This is like the data science Bible. Oop, can't see the book title. There you go. Thank you, Jason. Yep. Why do you remove dropout layer during inferences? So I don't really understand the question. So the dropout layer is kind of its own thing. So dropout layer is kind of its own thing. It's primarily used to add to prevent overfitting by getting rid of certain neurons within your system. I don't really understand. You mean the hidden layer? So essentially, you want your essentially when you create your like output layer, you want your output to fit like a certain paradigm. Like if you're predicting like a probability, you want it to. Yep. Thank you, Anirudh. Excellent. Um, so when you predict the probability, you would want it to be between 0 and 1. So that's why I use the sigmoid. I hope I answered that question. To choose a layer size. Can you post the resources in chat? Yes, I certainly can. Anirudh actually posted a link to the book on Amazon. Yep. Thank you, Anirudh. You're awesome. So good rule of thumb to choose layer size. Honestly, it's worth experimenting with to see like what your computational time is, as well as your accuracy or prediction power. But it's definitely a trade-off because neural networks already have like a difficult time with computational power. So essentially, I don't really have like a good rule of thumb to choose layer size. But what I would say is try to produce like if you're really concerned about it, try to produce an analysis on how a layer size is affecting your computational time and what benefit you're getting from that. Also, be sure not to overtrain. Add dropout layers if you can. What about the capsule net replacement for neural networks? I am unfamiliar with that, Anirudh. Again, Anirudh, you're fantastic. This is a great question. I am unfamiliar with that, but I would certainly love to learn a little bit more about it, or not a little bit more. I'd love to learn more about it. How to determine CNN hyperparameter and shape? We'll get to that. LSTMs require more memory to train, and if the data is not clean, a lot of issues, etc. How do I overcome those? Yep. So one thing you can do is LSTM. Yeah. A lot of questions. Any recommendations about PyTorch? It's a very tough framework to work with if you're not familiar with object-oriented programming. However, it will help you understand neural networks in a far deeper. It will help you understand neural networks in a far deeper way than Keras does. So yes, I love PyTorch. I just didn't use it for this particular talk because because I wanted to show you guys how all this stuff goes into action without having the requirement of advanced coding experience. But yes, I love PyTorch. I would definitely recommend looking into it once you've mastered Keras. In training, we use dropout and NN to overcome overfitting, but in PyTorch in production, they no grad, which in turn off batch normalization and dropout. Yep, pretty interesting. That's a really interesting point. I didn't go over dropout in this, but I would definitely recommend looking into it. It was one of my next steps. How to enhance our practical skills. I mean, where can I practice DL? All over. It's free. Just download Anaconda, get Keras into your system, and then you can find your data on Kaggle. Excellent. Yeah, data is not clean. How do we overcome those? So essentially, normalization is one great way to overcome it. Normalization of your data is like, particularly with the min-max scaler, can be very useful. The more memory, it's again something to keep in mind. If you're really strapped for it, like you can look into big data services or Databricks or something. That can be really useful for you. I think now Data or PySpark has a very good deep learning library that's worth looking into. But anyway, you can manage the number of cells that you use. You can aggregate your inputs, like maybe instead of days, if it's better to go with months. There's lots of different things to do to overcome those. But excellent question, man! You guys are an awesome audience. Fantastic questions. Now for the fun part, somebody jumped the gun a little bit. Going to convolutional neural networks. I'll try to get through this relatively quickly. So convolutional neural networks is a method that neural networks use to automatically pre-process unstructured data. So if you recall before when I was talking about neural networks don't need human intervention to pre-process unstructured data, this is part of it. So essentially, how a convolutional neural network works is that you can think of an image as a double array, as an array between two as a double array of pixel intensities. So you can kind of see it here. Like you see this is black. Anyway, it's a double array of pixel intensities. And when you have a data set of images, when you have a data set of images, you have a list of double array, a list of 2D or two-dimensional arrays. Now, basically, how convolutional neural networks work or the point of them is to reduce the size of your input so that when you're sending an input to your fully connected neural network, it's not going to overwhelm it. So basically, the entire point of convolution is to just continue to condense the size while extracting information from your images to turn that into a one-dimensional array and send it to the fully connected neural network. And you can kind of see the way it's doing that over here. So basically, features are first extracted in the convolutional layer with the convolutional filter. They're sent to the max pooling layer where it's further condensed. And then they're pre-processed into a singular dimensional input. And then they're sent to a fully connected neural network connected to an output layer. And then backpropagation ensues and everything, including the filters from the convolutional layer, are updated. So going into more in-depth on how the convolutional neural network works is essentially you have a convolutional filter that's a particular size, in this example to 3x3, that is essentially catered to identifying a certain quality about an image, like OneNote, for example, like edges, or you have the Gaussian to identify features more easily. But they come in a lot of flavors on how they're initialized. A window of pixels, of pixel intensities is selected, and a dot product is found between that and the convolutional neural net, between that and the convolutional filter, and that essentially and those dot products create what is called a feature map, and then essentially you can see the way the convolutional filter works. It moves in what is called a stride across the image and creates a feature map from that using the dot products. Padding, which are zero values around the edges. So this doesn't have any padding, but padding can be used, zero values along the edges of this image to properly to make the convolutional feature fit, or to properly identify images, or to basically create a larger feature map if desired. But you can use padding in the image in this process to aid your convolutional neural networks. I primarily use it just to make sure that we have a consistent square shape of our image that the convolutional filter can move across. And then an activation is applied to each portion of the feature map in order to, again, determine which features fire and which don't. It adds that layer of sophistication, that layer of nonlinearity to our convolutional filter. Then this is sent to what is known as the max pooling layer for further condensing. So in this example, essentially max pooling works in a very similar way in that a window moves across unique pixel intensities, or a window moves across the image to further condense pixel intensities. However, you can see that it selects unique pixel intensities when it pulls these together. Now, when the pooling and max pooling is an aggregation function that occurs between the pixels inside of this unique window. And in this particular instance, they're taking the max number from those pixels, but you can use the average. I haven't seen anybody use the sum. That seems reckless, but I've seen people use the average before, and tons of other different pooling algorithms can be used for this. But it's up to you. It's worth considering. There's a strong debate for each one. Once the pooled features are done, they're sent to the flattening layer, which essentially takes this two-dimensional array and turns it into a one-dimensional array, and then placed in a fully connected artificial neural network. So, excuse me. So from here, you can just refer back to earlier in the slide to where it goes, and essentially it just moves through that vanilla neural network like it's just a regular input, and then back propagation for each of the weights ensues, and even the filters are updated within the convolutional neural network. Now, I do want to get to next steps before, but let me see if there are any questions. Geez, lots of questions. Is max pooling really good for the model because we were making the system loss of information? Yeah, that's a good question. So again, Anirudh, you're on fire. Excellent question. So max pooling, so the entire point of yes, you can argue that there is a loss of information, but at the same time, the convolutional neural network doesn't reduce the dimensions of your image by a whole lot, and that could be problematic when you input it inside of a neural network of your fully connected neural network. It can take way too long to train. So max pooling is kind of there to take a little bit of that pressure off of your computer, which is always welcome when it comes to neural networks. But that is a really good question. Let me move up. So CNN hyperparameter shape. Yep. So the CNN hyperparameter and shape, you'd want to consider your input dimensions to be your image size and shape. Always make sure your image is square. Typically, that works a lot better. And then you want to have your feature map, the kind of your convolutional filter, the size of it. Sometimes what you want your convolutional filter to be. You want your activation function. Then moving to the max pooling layer, you want the size of your window. And then the flattening layer doesn't take any additional hyperparameters unless you wanted to. LSTMs require and skills. Any recommendations about PyTorch? God, some of the questions disappeared. Yes, recommend PyTorch. Where did the new questions go? Anyway, I saw like a bunch of new questions. I can't find Anirudh's question, which he asked. Really good. But let's go to the conclusion really quick. So from this, I'm hoping you have a strong understanding of the basics of deep learning. It's an incredibly complex field with limitless topics that you can just learn about for hours. Like you can write an entire book on deep learning, you still wouldn't even cover a quarter of what's out there. Um, Essentially, neural networks have an input layer that sends outputs to the hidden layer, and then that sends outputs to the output layer, which then calculates loss and then uses that loss to update the weights. CNN and LSTMs are some flavors. LSTMs can be used for problems that have dependencies like time series and text, and then CNNs can also be used to extract information from unstructured data like images and, hey, text. So now this kind of goes right into some of our next steps. There are so many. So every topic is a deep rabbit hole. Everything from activation functions. Like people are developing new activation functions every single day. Optimizers are a really cool rabbit hole to go down. It's so much fun to see all the different types of optimizers, how they evolved, how they basically the ones that are used most often. The one that I use most often is the Atom optimizer, and I see that used the most often. But going back and seeing how the Atom was developed and seeing some ways people are trying to improve Atom is extremely interesting. Um, you can experiment with different neural network architectures. Stuff like autoencoders and graphical neural networks are very good for recommendation systems. I recommend looking into that. Experiment with dropout layers, excellent for preventing overfitting. Convolutional layers with one dimension. We only went over 2 dimensions. You can easily use convolutional neural networks for text. Think about it. You can move the convolutional layer along your text, condense it into a feature map, pull your text, and then flatten it, and then you have a convolved text. Bidirectional neural networks, another useful iteration of LSTMs. You can use audio preprocessing for combined with CNNs for audio analysis. This is really cool. Python has a very good audio preprocessing library that forms images, and then those images can be placed into a convolutional neural network and analyzed. And then you can even combine different neural network architectures. Like I remember I've been looking into a lot of LSTMs combined with CNNs for video analysis lately. Really cool stuff. So that's the presentation. I have a little bit. I believe I came in a little late, so I have a little bit of time to go through the. Yeah, I thought the transform would do better than RN and LSTM and long-range context dependencies. Yep, transformers are really useful. That's a good question. They're yep, transformers is worth looking into. That can just be another tool in your arsenal for text. But yeah, like transformers are known to be like the improved version of those. But you can still use neural networks for your text if you want to. The best architecture for recognizing. Yep, that is a convolutional neural network that can be the best architecture for recognizing fingerprints. Well, let me see any recommendations. Well, sorry, famous libraries for deep learning: Keras and PyTorch. Keras/TensorFlow and PyTorch. Both are very excellent. TensorFlow is a lot easier to learn. Keras/TensorFlow is a lot easier to learn than PyTorch, but PyTorch is extremely rewarding to get under your belt because it will help you understand. It'll give you a better understanding of neural networks as it gives you like more freedom to develop them than Keras does. Yep. So I unfortunately don't, and you can contact me on LinkedIn if you would like. I unfortunately don't think we have a lot of time to go to do the dashboard, but let me just go through this really quick. These are some example of executions. Basically, for this one, you want to just when you first do your vanilla neural network, you want to make sure that all your numbers are numerical. In this, you see we first established the type of model we want to use with Keras. We add our dense layer and the number of neurons that we want to be a part of our input layer, and as well as our input shape. So this is what creates our first, excuse me, our first layer of neural network. You're seeing You're seeing the use of activation function here, and then it sends it to our hidden layer, as said before. And then we take that and we take that and create our output layer. We have one neuron here because we want a binary, because we're identifying a binary value. And our activation is sigmoid because we want a probability. So it's important to keep in mind what you want your output to be when you're creating your final neural network. And then when we compile it, we establish our loss function here and our optimizer. So this is essentially how we want our neural network to learn. And then finally, we train it and we define how we want our neural network to be trained. In this example, I want it to be trained over 100 epochs with a batch size of 100. And then we identify the data that we wanted to train it on. So very brief. We then create predictions. We interpret the probabilities as a decision, and then we validate. I went over an example of how to recreate your neural network to take in multiple inputs rather than just a binary. So you see this looks very similar. We have the same input shape. However, it gets different right here since we have four categories. We want to have four different neurons that we output this into, and we use the softmax function, which essentially makes all four neurons of their outputs add up to one, and we take the max of those outputs and we have created a decision from them. And so we establish our loss in binary entropy over here. Now for long-term short memory, long short-term memory, not long-term short memory, but we first take this, we read in our data, we create a date time. We want to normalize it using the min-max scaler. You can see each variable is plotted over here. Mean pressure is not looking so good. It looks very awkward. So in this example, we're going to drop mean pressure since we're going to be doing two examples, one with just a singular input, one with a multi-input. Then we want to pre-process our time. I'll go over this. You can take a look at this. I put a lot of effort into commenting this. Basically, when we create an input for an LSTM, we establish a number of steps we want, which is the number of iterations or inputs we want in a particular time series that we want to use as the input for the neural network itself. So like in this example, you can see we have 3 steps. So essentially, we have a collection of matrices that are three entries long. We have a collection of 1458 matrices that are 3 long, that are size 3 long. So, and then we have our 3 variables right here. So that's essentially what this is. So essentially, it's kind of similar in the way we input in an LSTM, except LSTM is a bit different in the way it's dimensioned. But you can think about it like we have a matrix. Our input is a matrix of matrices. It's not just a singular time input. So then we establish how many steps we're doing and how many features we have in our LSTM layer, and then we use our ReLU activation function. We send it to the dense layer into a hidden layer, and then we want to produce an output or a numerical output for each of the features that we have. So the number of neurons we output is going to be n features. So we have n features going into this neural network, and then it will produce n features out. And then our loss is MSE this time because we want numerical. Our optimizer is still atom, and then we choose the way we want to train. Sorry, I'm kind of speed running this because we have 5 minutes left. We train it. We then create predictions from it. So you can see we actually ended up predicting all 3 variables at the same time, and each input from each of the variables is actually dependent on each other. So not only did we predict multiple different outputs, but not multiple different time series, but each time series also has a relationship that affected the other. So pretty cool stuff. It's similar structure to a variable autoregressive. This is just an example of how we want to, if we only want to predict a singular time series. So you can see we have a slight difference here. This one, because we only have one feature. However, we're still having three time steps per input. We input this in, n features equals 1 is the change, and then you can see the mean temperature predictions for the next year, and we have a really good mean square error. So cool. Now for convolutional, this is where it gets a little hard. I'm going to have to rush through this. I'm sorry. So first we establish the directories where we have our images, and we use this OS listier to get the list of directories. And once we're done pre-processing our image directories, you want to make sure you have the entire directory here. Otherwise, it'll say none. Once you have that entire directory, I shuffle them up because they're so separated. But we'll have the full list of directories down here, pre-processed full directories. You can see data dog cat test set cat, and then and then you have your image right here. It's important to have the whole one, otherwise you'll get none. Here we read in each of the images using the library CV2. CV2 is a very good image preprocessing library in Python. I recommend it. It's very simple to use. We want a grayscale, so you can actually use colored images, which are in the RGB scale, but it greatly increases your computational time. So I just use grayscale for this. We read in our images, and then we resize it to 2424. You can do a different size. However, you usually want to make sure that it's square. Some CNN architectures can handle it, but it's important, but most can't. And it simplifies your life heavily if you just it simplifies your life heavily if it's a square image. And then you normalize it by divided by 255 to normalize it. So essentially, pixel intensities between 0 and 255. So this reduces your intensities in your image to a range of 0 and 1. Makes it easier for your neural network to predict. You then make sure that you have this 1 at the end of your array. Basically, that makes it the neural network is expecting each image to have 4 dimensions. So when you there's a reason for that, primarily like in video analysis and stuff, or the number of channels you have, or for colors. You like this number would typically be more than 1, but however, since we're on grayscale, it's just going to be 1. But if you want colored images, like you can shift that to 3 for your RGB, and then train your neural network like that. But we're not using that for this example. And then and then each of these, we got the label dog and cat from our image name, and then we turn Y into that array. Then moving through this, you can see like this train shape, test shape, and then within this sequential diagram, we first establish the number of neurons, or the number of filters that we want. Our input shape is 2424.1. That's the size of our image. Our kernel shape is 3.3. We want a 3 by 3 convolutional filter, and then our activation function will be ReLU. Our max pooling layer will be a 2 by 2, so it'll be a unique. It will be aggregating pooling 4 pixels at a time throughout each of that. It'll flatten in this layer, and then we send it to this this fully connected neural network at the end. We have our ReLU activation function right here, and then we have our sigmoid because we're predicting a binary. Then we have our binary cross entropy loss since it's categorical, and then our optimizer atom, our batch size, and our number of epochs right here. It trains, and then we're able to predict we're able to predict labels based on image inputs. So that's pretty cool. And then we have our accuracy. So 1 minute, 1 minute to spare. I had this dashboard that we can use to further execute this neural network. This is based on the CAR value set for the deep learning. Basically, you can use this model.save and model.load all the way up here. Sorry about that. This model.save and model.load right under here. Yeah, right under here. And at model.save, model.load. You can use this to save your neural network and turn it into a dashboard like I did over there. And this is the code for the dashboard. I'll send this to you. I didn't have time to go over it today. I knew I'd be pushing it with the dashboard, but yeah, that's the deep dive and deep learning. Can we get a sample? Yep, you certainly can. I will put it in a GitHub repository and send it over to be sent out to all of you. But yep, you guys were a fantastic audience. I really thank you for for bearing. I'm still getting used to using this platform. Really thanking you for bearing with me, and I really appreciate your time. And I hope you established a good basis in machine learning. You all were fantastic. Thank you. And I think that is it. Do I have slightly more time, or is it about to cut me out? Which GitHub repo? Yep. I'll be sending it out. I'll be producing the GitHub repo and sending it out shortly. But you all were fantastic. Special shout out to Anirudh. You were the MVP, asking fantastic questions and posting that link in the chat. That was really helpful. You all were a fantastic audience. Again, like I love doing this. I love doing this because the audience at these data DS Connect conferences are so amazing. Like the amount of thoughtful questions I get is unbelievable. Like the amount of thoughtful questions I get and useful inputs from you guys is unbelievable. And it's just an honor to talk to you all.